Okay, we're going to take a look at an application of normal distributions. One of the reasons that normal probability distributions are so important is that many real-world applications can be modeled closely with a normal distribution. Lots of examples occur, like heights of people, scores on large standardized exams, like IQ tests, for example, many things that you're manufacturing, such as weights of something, masses, diameters, lengths. Lots of different things are approximated with a normal distribution. For example, we're going to look at one here where annual rainfall in a particular area is modeled pretty well by a normal distribution. This particular one is going to have a mean of 29.55 inches and a standard deviation of 8.5 inches, and let x be the amount of annual rainfall. So we're going to use this model to compute some probabilities. So notice the first thing I'm going to do is take 29.55, store that as m. And notice I hit the store button was down here in the lower left. It's the STO button. It's one key above the on button. And to get the letters, you push the green alpha button first. So you press 29.55, store alpha m, enter. And so now anytime that we pull up m again, like we just do alpha m, it will be that value. Similarly, we take 8.5 and store that as s. Okay, so let's see what's our first question. What's the probability then in a randomly selected year the rainfall will be between 19 inches and 25 inches. So when we're computing probabilities, we're going to go second variables to get distributions. And actually, on all of these probability problems, you're either going to use 2 or 3, or if we want to draw something, we can go right arrow to draw and use the first one there. We should never really have to use number 1 unless we just want to draw the bell-shaped normal curve without shading probabilities, shading areas, which of course correspond to probabilities. So we can always use number 2 here if we're trying to compute a probability. So we want to go from lower of 19 to an upper of 25, and we want to use our mean of, well, m, and our standard deviation of s. So if you just store those as m and s, we can get them that way. Or if you'd rather, just go ahead and instead of the m, type in 29.55, and instead of s, type in 8.5. And we push enter, and this will give us what we want here. So that is 0.188952873, or about 18.9%. We try to use a percentage. So I'll make that a little bit bigger so you can see that. Hopefully a little bit better. If you can't see it on the one on the right, maybe now you can see it there. Suppose that rainfall below 10 inches per year results in a very dangerous drought conditions. What's the probability that in a particular year we will have these conditions? Well, that's a probability really from negative infinity up to that value of 10. Before I do that, let me go back and show you something on this previous one. I can actually if I want to see the graph that goes with that, I can go to distribution, again, second variables, go to draw, go to shade normal, and basically enter exactly the same numbers I did last time, 19, 25, alpha m, and alpha s. And now this will graph it and shade it. Okay, unfortunately I had some stuff all there already, so let's clear that out. Shows you why you always want to clear your drawing when you're done. And if I quit, if I just hit enter, it'll execute the previous command. And so there it shades it and graphs it. Now that might not be the best window, so let me change that window just a bit. The bottom of 0 was okay, but I think we want to go out a bit further. Let's go out to 50. Maybe mark it off in tens. And it looks like we didn't need to go nearly as high. Maybe 0.1 will be enough. If we're going to do that, let's make this 0.07. Let's see what that looks like. And now let's quit and let's shade that normal again. Yeah, that's a prettier looking graph. And we have the area computed, the same number, notice, that we did getting before. So if we just want the number, use the normal CDF. If we want to graph it, use shade norm. Alright, so similarly on this one, now let me go ahead and clear the drawing. Always clean up after cells here. Okay, so suppose that we have the drought conditions 10 inches or below. So what we want to do is go from negative infinity up to 10. Now, for this to really work, what we want to do is really use negative infinity, but we can't really enter that in on this particular calculator, so we have to use something below which the area is so small that it doesn't really affect our numbers. So if you go 10 standard deviations below the mean, that works. So this is basically what we want to enter in here. So if I go to distribution, normal CDF, we want to go from the mean minus 10 standard deviations below up to 10, and with that mean and standard deviation, so M and S there. And so that gives us the value that we want, 0.107240811, or about, if we did percentage, about 1.1%. So about 1 year out of every 100 we're going to reach these drought conditions. Okay, we can also draw this one if we'd like. See, I already cleared the drawing, so I can go to distribution, second variables, right arrow to shade norm, and enter the same things. And in fact, I've got a little shortcut. Let me want to show you this. If we just go second enter, that'll give us exactly what we had before. And if I can just change the command at the beginning from a normal CDF to shade normal, I can do that just like this. It saves me a little typing. Get lazy sometimes, so. And we will do that. Okay, and it's so small here that we really can't see it. It's shading up to, I think this is 10, 20, 30, 40, 50, so it's shading up to right here, but the shading is so small on this scale we can't see it. If we zoomed in a bit on that part of the graph, we might be able to see it, which we can do. Let's try it. Zoom box. Let's just start it. Right in there. And of course it's not going to be graphed, but if we draw it back now you can see that part of the graph shaded if we zoom in. Okay, and so that gives us the area that we're looking for. Okay, and that was shade norm. Yep, shade norm, and the rest of this was the same as this up here. Okay, and that gave us the second picture that you see there. This time we're talking about flooding. Flooding of a reservoir will likely happen if the annual rainfall is really big. In this case we say 54 inches per year is the threshold there. So we go from 54 up to infinity. And so let me put my window back where I had it before. Okay, and let's go ahead and draw it first this time. So we'll go to here, shade norm. Let's clear this out. Shade norm. Okay, so we're going from 54 up to infinity. Well, we can't put in infinity, so we're going to use alpha m plus 10 alpha s. And that's with that m and s, that mean standard deviation that we have stored. And it's going to be, well, this is 50 right at the end. This is actually off the screen what we have shaded, but it's rather small. But it still, notice it still computes it even if it is off screen. And we can also find it directly by doing normal CDF, second distribution number 2, of 54 up to m plus 10s, and with our particular m and s. Again, the same number there, you noticed. That's the same number that we just did. And so that turns out to be, so this is a right tail area. It's actually a little bit off the screen here, so just the tail going out here to the right is what's actually shaded. So in other words, about 0.20%. What's the probability it would be between drought and flood stage? Okay, well, drought was 10, and below 10, and above 54 was flood. So we want it between 10 and 54. We can do that by, it's going to be almost all of it, but let's figure this out. Go to number 2, from 10 to 54, with our particular m and s. Okay. Make that a little bit bigger for you to see it. And in this case is 54 for the upper bound and 10 for the lower, and that's over 98%. About 98.7%. And again, if we wanted to shade it, we can. We can go to shade normal and do the same thing. Actually, I'm going to shortcut again, second enter, and change this from normal CDF to shade normal. It's not a bad idea to do both if you've got time, because sometimes if it's, you can see if it's shading the part that you want, gives you a nice visual, and it's shading between 10, which is right here, and 54, which is just slightly off screen, but same area. What proportion of years, what is the proportion of years that the rainfall is within 5 inches of the mean? Well, so let's see. Let me clear my drawing. And clear the screen, so we'll start fresh. Okay, so again, this is a distribution, a normal CDF to compute probabilities, and we're going from the mean minus 5 inches up to the mean plus 5 inches with our mean of M and standard deviation of S. Again, you can figure out what these numbers are and type them in here if you want, but that gives us our probability that we're after. So we're going from mean minus 5 to mean plus 5. And (44.4%). And again, if we draw this, this will be in the middle. Let's see what this looks like in the picture. So actually, pull that back up, change the normal CDF to a draw normal by going second distribution, draw, shade normal, and enter. And notice that we get a region centered up on the mean there, centered up right in the center, in the middle, and this is what we want. Same value. We sometimes do get a couple more digits at the home screen, but most likely you're not going to need that many digits anyway. Our model's probably not that accurate anyway. What's the proportion of years that the rainfall is more than 15 inches away from the mean? Well, it's 1 minus the probability. Okay, let me put it this way. This is the probability that x is less than the mean minus 15, or x is greater than the mean plus 15. Well, this is also equal to 1 minus the probability that x is between m minus 15 and m plus 15. Like that. Okay, and we can get that as normal CDF of x m minus 15 to m plus 15 m s. Let's see what that is. Clear my drawing, go back to the home screen, clear that, normal CDF 2 m minus 15 to m plus 15 mu and sigma. There we go. And we can shade it if we would like. We already got some shading, so let's clear that. Okay, shade it by actually going back to here, pull up our second entry, and going back to the beginning here. And change it to a shade normal. Now, okay, so that is that's the part that's shaded there. That's what it's not. What we want is the outer parts shaded. Okay, so what we need is 1 minus that. So I need 1 minus that answer. Should have done that on the same line, but I can still do it from here a couple of different ways. I'll just go back and do it from the home screen. I can either do 1 minus the answer I had up above, or I'll just do it again. Let's save a little typing here. Okay, that's what we want, but we want to insert a 1 minus in front of it. Alright, now we're talking. That's what we need. Or in other words, about 7.8%. Okay, if you really want to graph that, it's a little trickier, but not too bad. I bet you could figure it out. Let's clear our drawing. Okay, but what we have to do is shade the two pieces separately without erasing between. So I can go to Draw, Shade Normal, and then I want to go from negative infinity. Okay, so we're going to use mu minus 10 sigma. Didn't get any element in there for some reason. Okay, up to the mu minus 15. With mu and sigma. Now that shaded the little left tail, but there's also a right tail, and the area you see there is only for the left tail. Now of course if we double that, we're going to get exactly this because of the symmetry involved. So that's another way to find it. We could find just one tail and then double it because we have both tails now. But if we want to graph the other tail, be sure not to erase this one, and we'll graph the other one with it. So I can quit. Do another shade normal. This time the left side is going to be mu plus 15, and the right side is going to be mu plus 10 sigma. I believe that's going to work. Yeah, and that's our approximation of infinity. So now if we hit enter, that'll graph the right side, and notice we see the symmetry involved. Each of these little two-tailed regions have the same area. So this is a two-tailed situation. I'll make a note here that the number one tail only for that number, double get the two-tailed area. What's the 90th percentile for rainfall? Okay, so up to this point, the first 6 are doing probabilities. So notice we use shade norm if we want to draw it, and normal CDF if we just want to compute it. The rest of the problems here have to do with inverse probabilities. So remember that an inverse probability, you're giving a cumulative probability, that is the probability from negative infinity up to the value that you're looking for, and you know that probability, you're trying to find the x value that goes with it. Okay. So on the PDF, that's going to be an area from forever left up to the value that you're looking for. The area or probability is known. What you're looking for is that x value on the boundary. On the CDF, what that is you know the y value and you're trying to find the x. So I'm not going to graph this one. I'm just going to go and do this with an inverse norm. So this is going to be the easiest way to get this particular one. And the 90th percentile, we know the area below is 0.9, 90%. And then we give it the mean and standard deviation so it knows which normal curve we're dealing with. And it will just give us what we're looking for. That's an x value. So in this case, x values have units that are inches. The answer here is just say 40.4 inches. So notice a percentile is always, you know the percentage, you know the cumulative percentage. What you're finding then is the x value that goes with that. Okay, same thing as here. We have the cumulative percentage. This is probably that x is less than c. We want to find c. So it's exactly the same kind of problem. We just take our previous entry, and instead of 90%, it's 45%. So we put 0.45 there, and that will give us the value that we want. So here we know that C equals 28.48 roughly. Alright, now this time we know the cumulative we don't know the cumulative probability. What we know is the right tail probability. Inverse norm is always used with the left tail probability. Of course, it's pretty easy to find. What we need is the probability that x is greater than c. Well, that equals 1 minus the probability that x is less than c. Okay. Well, let me do it the other way around. Probability that x is less than c is 1 minus the probability that x is greater than c. So that will be 1 minus 0.05, which is, of course, 0.95. So 95% of the area is to the left. Only 5% of the area is to the right. So we can find c then as the inverse norm of the 0.95 with our mean and standard deviation. Okay, so let's do that. Inverse norm, but we need to put in 0.95. So notice that we had to do our subtraction to figure out the right percentage to put in. We did that first, and then it's just a straight inverse norm for the answer, which is about 43.53125582, and that's inches. Okay, the last one, C, is also inches, and we found that by inverse norm of 5, comma, M, comma, S, just in case you can't see everything there on the screen. And up here we found inverse norm. Found it that way. Alright, let's continue on. We know that the probability that the annual rainfall is within C inches of the mean is 90%. What's the value of C. Okay? Within C inches is 90%. So what that means is we know that the probability that if we take the mean, well, this was just M, got it stored as M anyway, minus C is less than X, is in turn less than M plus C, we know this probability is 0.9. Alright. Now this one requires us to think just a little bit. So let me do a little sketch here to get a rough idea. Okay. Let's do it this way. Okay. So we have our axis here, and we have our normal distribution. Okay, with our mean right here in the middle. Okay, and here is mean plus C, and over here is mean minus C. And this area right there is 0.9. Now, if we look at this area, I'm going to call this 0.9p. This area is p over 2. Or in our case, 45%. Why? Well, because this is symmetric. But what we really need to see is that the area all the way to here, that purple area, is the cumulative probability, which is p over 2 plus 1/2, because it's half below here. So that area is 1/2. And this area right here is the p over 2. Okay, then that's the cumulative area. So, what does that give us? Well, that gives us that the probability that X is less than mu plus C is, well, let me just write it this way. P over 2 plus 1/2, 0.5, where P is 0.9. Okay, so in our case, that's 0.9 divided by 2 plus 0.5 is 0.45 plus 0.5 equals 0.95. So that means if we do an inverse norm of 0.95 with this mean and standard deviation, what we will get is mu plus C. So to solve for C, it is that inverse norm minus mean. So here we go. Easy enough to do that. Let's see. Inverse norm 0.95 up to with a mean of M, standard deviation S. And then we still have to subtract off M. So, oh, that doesn't look right. Oh, I did norm. I didn't do inverse norm. Okay. No wonder it doesn't look right. Inverse norm. There we go. 0.95, M, comma, S. There we go. 2 commas. Oh, and then I forgot, I've still got to subtract M after that anyway, so alpha M. Okay, I think I've got it now. There we go. So that's the value of C. So C is 13.98125582. Of course, we'd probably round off somewhere. Okay, continuing on, similar problem. What interval centered at the mean contains the annual rainfall for 95% of all the years? Well, again, we see if we sort of draw this out and sketch it, that we're looking at a normal curve. There's the mean, and we have somewhere over here as mean plus C, and here we have mean minus C, and we know that this area is 0.95. Well, think about that. That leaves 0.05 split evenly between these two areas. So that means this one is half of that. 0.05 divided by 2 is 0.025. And this one over here is also 0.025. Well, that makes the total area to here 0.95 plus 0.025 is 0.975. So alright, so that means the cumulative area, if we do inverse norm of 0.975 with that mean standard deviation, what we'll get is the mean plus C, and which will actually be the upper end of our interval. And if we do the inverse norm of just the 0.025 with that mean and standard deviation, that'll give us M minus C, which is our lower end point. So these are the two numbers we need. Alright, let's see what we get out of that. So we can do distribution, number 3, inverse normal, and we want 0.975 with our particular M and S, not X, and that'll give us our upper end. That's this guy right here. That's mu plus C right there on that end. The right end, 46.2096938. And then we can do the same thing, but change the 0.975 to 0.025. Oops, got my decimal. There we go. And so that gives us the interval that we need. So the interval we need is the interval from, I'll round off here a bit, 46.2 inches up to 12.9 inches. By the way, notice these are values on our horizontal scale, which in this case is inches of rainfall per year. Okay, maybe I've got one more. We know that the probability that the annual rainfall is farther than C units from the mean is 1%. What's the value of C? Okay, again, it's as always, it's pretty useful to at least get a rough sketch, even though this may not be a real accurate looking picture. I can get a rough sketch of this. And I know that if the mean is here we have mean plus some value, mean minus some value, and this part that's far out here together is 1% or 0.01. Well, that means you have half of that, half a percent, or 0.005 here, and 0.005 probability or area there. Okay, so that means up to here we have, well, 1 minus 0.005 or 0.995, and below here we have 0.005. Okay, so if we want to find these values, mu plus C and mu minus C, I know that mu minus C is just inverse norm of 0.005 with our M and S, if we want to find that. Mu plus C is inverse norm of 0.995 M and S. And C then is, well, what we get from mu plus C minus mu. Okay, so let's go ahead and figure these out real fast. So, inverse norm, 0.005 M and S. This is our lower bound, which is 1. CDF. I didn't mean to do that. I thought I was doing inverse norm. Let's try it again. It should be number 3. Yes, there we go. 0.995 M and S. Okay, that's our lower. And our upper is the same thing, but we replace that was the upper, sorry, that was the 0.995, so that was the upper. The lower is we replace the 0.995 with 0.005. There's the lower, and let me get back to the one that had the upper. There's the upper, and if we subtract M from that, we'll get our value of C. So, whoa. Okay. Well, that's what I want, but I don't want it up there. Let's see if I can get it down here somewhere. Okay, here we go. And let's finish this up here. Alright, so that is, so the interval is from 51.4 inches up to 7.66 inches, and C is 21.9 inches. So the 51.4 is the mean minus 21.9 inches. That's backwards. 7.66 is that. And of course the bigger number has to go on the right. 51.4 is the mu plus 21.9 inches. Alright, that gives you some examples of working with normal distributions.